Okay. Good afternoon. I'm Yu Yu Chen, and today I want to share the preliminary result about specific attenuation for QPE with the German C-band radar network. And from the earlier talk, we already know that RA algorithm is highly recommended because it keeps the advantage of RKDP but less noise in light range and suffer less from the spectral degradation. And also from the previous talk and the studies at X-band radar, it shows sensitivity of alpha value to DSD variability. And this alpha value is the key parameters to estimate specific attenuation in the fit method. So what delay do is derive this alpha value according to the range type, which is categorized by the change of LDR with reflectivity. And it is so-called LDR slope, and it is immune to a radar system bias. Moreover, the range retrieval derived from the vertical specific attenuation was proved to be less sensitive to the DSD variability, and we expect it will provide a higher accuracy in areas of strong attenuation compared to the one derived from the horizontal specific attenuation. But we will face more challenges when RA is applied at C-band radar. It is because alpha value is more sensitive to the DSD variability, and its dependencies on ZDR is non-nomotonic. And when we use the LDR slope, it will be more complicated by the stronger attenuation and the resonance effects. Moreover, there is an enhanced sensitivity of the coefficients in RA relation to DSD characteristics. So to solve the problem, for example, in tropical area, RA relations are derived depending on the range type, and in the middle and in the mid-latitude, it was found that RA scatter plot is much narrower than those of RA for heavier continental range. So according to this fact, as well as the better applicability of RKTP at shorter wavelength and the shortcomings of RA in range mixed with health, in this study, we will combine RKTP with RA relations to estimate rainfall. The data I use in this study include this disoriented data from DWD and from our institute. Around 84,000 DSD are collected and used to investigate the impact of DSD variability on the parameters of QPE retrievals via the team metric simulation. And we also use range engagements and Radalan W product for the evaluation. And this RW product is hourly QPE based on reflectivities, but adjusted to the range gauge measurements. And about the radar data, we use, of course, DWD C-band polarimetry radars with the precipitation scan strategy, which elevation is terrain following to avoid the partial beam blocking problem. And 5 cases were observed by 10 radars in the central and northern part of Germany, and 4 of them are the convective cases, which are catalyzed by the strongly organized school line with health, and the other one is the stratiform events. So here we follow the similar concept which have been done at X-band radar, that is derive alpha value from the LDR slope. And here we use NW, the normalized raindrop concentration, to classify precipitation over Germany into 6 classes. And then so we can derive the alpha value and the LDR slope K from each class via these 2 equations. So we can further determine the relationship between these two parameters, here shows the result. We can see that for the vertical specific, the vertical alpha value shows a similar tendency as the one we can see from the H-band radar. But the one from the vertical variables, we can see it increase after. And then now we only need to derive this K value from the radar observation. And we use the data with the attenuation correction and the data with VDP smaller than 30 degrees to reduce the attenuation related uncertainty. And the K value can be derived by a linear fit and is renewed scan by scan. And C-band radar is VDP bump due to the non-uniform beam filling, and it could be more severe at C-band radar with the combination of the Renaissance effect. It shows an example here is the radial profile of each radar variables. We can see there's a VDP bump here, and then the KDP we derive directly from this VDP first increase abnormally and then with the negative value following behind along the rate. So to solve this problem, we try to estimate the KDP process from the attenuation, corrected reflectivity, and the total span of VDP. So we will replace the original KDP if the reflectivity is between 40 to 55 dBz and the original KDP is smaller than 0.25. Besides, we also exclude the data from the integration in the fit method if the reflectivity is larger than 40 dBz, where is the potential existence of hell to prevent extremely high specific attenuation value. And here shows the set of rainfall retrieval I use and compare in this study. Basically, RKDB will use when reflectivity is larger than 40 dBz. And for the Z-based algorithm, I will also compare the result which is derived from the original KDP and the one with KDP process replacement. And for the A-based algorithms, I will compare the result with the different hybrid threshold, that is KDP applied when reflectivity larger than 50, and the one applied when reflectivity is larger than 40 dBz. And also compare the result with and without the adjusted alpha value. And here list the run rate relationships I use in this study, and they are all derived from local major DSD data. So here's the result. It is the convective cases, and we can see for the different color bar represent the different variable-based retrieval. And from the left to the right is the same order as the table I showed from the previous slide. So here we first focus on the Z-based algorithm. For the traditional RZ relation shows, of course, the highest normalized root mean square error and the lowest correlation coefficient for all of the cases. And if we combine with our KDP, no matter which KDP we use, it can further improve the score. And for the A-based algorithm, if we first check the one without alpha adjustment, that is the first and the second bar in blue and in green color, we can see that the one derived from horizontal specific attenuation shows the larger error compared with the one derived from the vertical, especially especially for the normalized mean bias. But after the adjustment, that is the third bar in green and blue, we can see that both algorithms shows the comparable performance, which demonstrate that the adjustment of alpha value play a role and can reduce the DSD variability impact on RA relations. And here shows the our QPE product derived from the vertical specific attenuation and compare with Radalan RW product. And it shows a good agreement, which show the benefit like our product just based on the radar observation and is quite comparable to the one adjust to the rain gauge measurement. So here we further take into the normalized mean bias as a function of 3-hour accumulated rainfall classified into 3 different rain intensity. So we first again look into the Z-based algorithm. For the green line, which is with the KTP process replacement, the arrows at each rain intensities are between or smaller than the other two. And it always shows a lower arrow than the one derived from the original KTP in the moderate and heavy rain. And for the A-based algorithm, if we first compare the orange line and the blue line here, which use the hybrid threshold of 50 divisits reflectivity, and the one is 40 divisits, we can see if we use the one derived from 40 divisits shows the smaller arrow in the heavy rain. And it can be explained that the alpha value, the lower alpha value used in the heavy rain lead to the further underestimation. And if we compare the algorithm with the one with just the alpha value, that is the green one, we can see that it shows the smaller arrow in the light rain. And even though I just showed one example, but all of the convective cases show the similar tendency. But the improvement is achieved only by reducing the bias, and there's still an overestimation in the light rain and underestimation in the heavy rain. And it can be explained that a scan-based alpha represents an average value, but cannot take care of the various precipitation type which occurs within the scan, and then limited the improvement of normalized Loomis square error and the correlation coefficient. So the rate-based alpha is suggested in future work. And there's another problem in the area right behind the hail core with strong attenuation. That is, all the products shows several underestimated bends along the rate here, which we did not expect from the phase-based algorithm, especially for the one derived from the vertical specific attenuation. And it is because, like, if we ignore the FDP cord and directly connected the pure rain segment into a pace, so we miss the attenuation from the cell, which should be propagated to the bin, the later bin, and then lead to the underestimated rainfall in the later segment. So in the future, the integral process should be reset in each pure rain segment for the fit method. And here is the result from the Tradiphone case. We can see the Z-based algorithm overall perform much better than the one derived from the specific attenuation. And all of the product underestimate the rainfall. And this underestimation can be caused by the less less sensitive VDP in stratiform event or the smoothing process of VDP or too low alpha value used in this study. I think it is because the embedded convective self in the stratiform case may lead to the lower alpha value, while most of the radar beam are dominated by the stratiform. And again, we can see the larger error from the algorithm with alpha adjustment again suggests the necessity of the rate-based alpha. And here is the rainfall map from our product and also the Radlan RW. We can see that in some radar domain, there is a partial beam blockage problem with an underestimated rate here. And it demonstrates the benefit of RA again, and it will be helpful in the southern Germany where it's mountainous and the terrain following elevation cannot really completely avoid the partial beam problem. So here's the conclusions. If the KDP process replacement can further reduce the error in the moderate and heavy rain compared to the one derived from the original KDP. And after the adjustment, algorithms derived from horizontal and vertical specific attenuation are quite comparable. And our QPE products are quite consistent with RW product, which is already adjusted to the rain gauge measurement. And a phase-based algorithm further mitigate the partial beam blockage problem. And for the future work, net alpha value along the rate or within the segment, and the segmentation of the rate in the case of how rain containing large rain or hail is needed, even though we know we will face more challenges at C-band radar. And also, we need to take small stratiform case in the future to solve the problem, to solve this underestimation. So thank you, is my talk, and this is the Hello.
I just realized I'm still muted, sorry. I said thanks a lot, you, for the nice presentation. And we have some time for some... Are there some questions? If not, I have already one. Since we have, there's a plan to include also the ray-based alpha estimation and so on, or even more detailed refinement like the segmentation. I now come back to the idea from Yan Chang at the beginning, or two talks earlier. She also suggested this, how was it called? Maybe she can help me here. The adjusted RA with an alpha naught, and then this additional, it was somehow the RFA relation, and at the end there was this factor alpha adjusted divided by alpha naught. So that is also somehow a strategy, a new strategy to include these variations in the alpha variability. So now, yeah, a discussion point or a question is, so are there already some results or some clues on what is now, do we know which strategy is better, the ray-based, efficient segmentation, and so on and so on?
Yeah, as I know, she derived this alpha value from reflectivity only. I mean, and then I think she classified the rain type in advance, like the marine, the convection, and continental. And so if we want to follow it, or we think that is the better method, then we need to develop our own algorithm to classify the rain type, right?
Yeah, Yan Chang is still in the speaker room. Maybe she also wants to comment on that.
Yes, this is Jian. Yeah, I think you may use your alpha knot to approximately identify your rain regimes. That's what we did with our alpha adjustment. Is we based on the alpha knot to decide we are in which dominant rain regime. Then we
okay. That is
apply
used
the
as a
alpha.
classifier also. Okay.
Yeah. Yeah.
And this adaptive alpha, which is in there, that is then that was based on these simulations, right? You showed this.
Correct. Yeah. The alpha adjustment as a function of z was simulated from DSD data. Yes.
And do you have already some experience, or did you compare to this more than what Alexander presented, for example, to do instead this ray-based, or are there already some comparisons available, or
Not yet, but yeah, we can for the next work we can compare. No, we haven't compared with the radio based. I have a minor concern with the radio based alpha because the rainfall distribution may not be that nicely just sectorized. So in a radio, they might still be two different regimes.
Yeah, especially in these. So I suppose in these very heavy cases who you faced already with these real hail cores, then probably we cannot do anything else than doing this segmentation, right?
Yes. The case I showed with that wide spread stratiform with a leading convective band. I think the reflectivity showed the two different regimes pretty nicely. Then with alpha naught, we know that the stratiform area have a pretty good warm rain type precipitation efficiency. Then in the convective area, the reflectivities are much, much higher. And then we can use that simulated alpha Z relationship, trying to tune down the rate in the high reflectivities area.
Yeah.
That's kind of the logic behind it, yes.
Yeah. Okay, thank you. A lot of more to explore, as usual.
It's always when we come to this local, smaller scale variations. That's a challenge.
Challenging task. Yeah. Are there more questions around? Did not check Slido again. At the moment, I don't see something.
I think that's fine.